Yes. So, yeah, Hannah, the floor is yours.
All right, thank you, Martin. Good morning, everyone. I think, can you hear me well, I think?
Yes.
Okay, so as Martin said, if someone wants to join to CosmoOps organization on GitHub, please let me know. I will share my screen right now. Okay, I think you can see my screen here. So if you're not familiar with GitHub, this is the organization from CosmoOps. And here you have access to many private repositories. And basically, I'm mainly developing on this SLComp repository. It is private because it's private in the organization, and people who do not belong to this organization cannot access this to the repository. However, this should be in public soon. And yeah, let me show the repository also. Okay, so just to give you an overview, this is the repository I have been developing since we started this project. I create this logo here because it's nice to have a logo. But basically, the repository is structured like this way. I put some code here using the project, and then in the data, I currently the way that I add the data was very like manual process. I have some ideas to optimize this process to getting the data. So for example, if you want to add data from a new paper or a new survey, I have an idea on how to optimize this, but you are very welcome to help me, to develop to work on this project in especially in this repository, because as long as we have many collaborators, we can make the things here more robust. So basically, in this folder two, I add all the data from the literature. Just to give you an example, so since this is exhausted, uh, I put all the data from many papers that I add in the work, including Masterlin's database, all the data itself. So yeah, we always can make this more robust. And then after processing the data, so if you recall, the Last-Peru database is composed by 4 catalogs. One, it's mainly built on the data from the literature, which is the 02 database here. And then the other catalog is made by cross-matching the data, and that is. And then the last one, it's consolidated data, where I add all the data together. So currently this database is not like a SQL. So I did not include this in a, so for example, in a SQL database or MySQL or Postgres database as a standard. So you can think this, which it is, a big table of tables. So you can access the data. So if you go here and then if you want the database, you can see this is the CSV that I merge all the data together. I don't think, let me see if I can open this here. Yeah, so this is the all the lines from the database. It's yeah, it's the way that I added. But if you want to contribute to this project, you're more than welcome to include this into a Postgres or MySQL database as well. So you have that CSV file that contains all the data from the literature together. In this cross-match folder here, you find the data from the photometric in spectroscopic matches that I mentioned earlier on Tuesday. And the consolidated data is the CSV file, which contains all the columns that all the queries, and all the data is here that I'm showing you. Also, let me go back. Let me go back to the README file. And in this folder here, I process all the cutouts from that I found. Also, again, this process is not automatic, so because I have to make many preparations until you have the final results that I'm going to show you later. And there are some notebooks here that you might, if you are interested, you can look at this notebook. There are some plots that you might find useful. I try to make everything reproducible, which is good. So if you find any error or something of logic, please let me know because this make the project more robust. Okay. So in this folder 03, I process, so I gather all the fits file and then perform the cutouts because usually in many surveys, they provide the information in a huge patch of the sky. But in this way, so giving the coordinates of the object, I go there and then cut the image. So you can see a small square of 20 arc seconds or 4 arc minutes. And also I process the file using Trilogy software, which it makes the images prettier that I'm going to show you in the dashboard. So in this folder here, I will present the dashboard soon, which is this this GIF here, which also please, if you have any idea on how to improve, please let me know because it's very it's not good enough. I think it's very simple, but we can always make it better. And all of this is built in Python. So if you have an experience Python and if you would like to contribute to the project, you're more than welcome. And the footprints, I showed all the footprints that I mentioned in my presentation. So if you want to make a plot from the footprints of the sky, you can go to here and then see their recipe. There are a lot of notebooks inside of this folder. And the applications, there are some modified gradient tests that I mentioned. I will show an example on how to get the data and select the objects for an observational proposal based on the data from the database. And yeah, so if you want to quickly explore the data, you can click here in the dashboard link, which is here. Let me share with you in the chat. I have some questions. Okay, so dashboard. I will add here. So if you go to this website, and so for example, the way it's structured, I structured based on the reference. So if you know any of this reference, for example, many of you use data from Cal et al. 2015. So I can select the data here, and then there are 118 objects in this catalog. And here I added all the images together. So if you want to make a quick view of this of each system, and so in this line here, I add so for example, all the data available in many references. So that is why I have this slash because so for this object specifically, let me move this to this window. It's found on all of these references with all of these values reported for each reference. But if you want to use the consolidated catalog, you might see only a single entry because that's the purpose of this consolidated catalog. And here you have a processed cutout for this object. Of course, you have access to the fits file, but we also added the images, the processed images for you because it's very convenient if you want to perform, so for example, for follow-up observation and select some systems. Okay, move on to, let me go back to repository. And finally, Okay, all of this data is stored in a simple storage system. So right now I'm using a MinIO service. This is basically, it's a way to put all of data together in buckets, and then you can access to the interface. So I go to this service here. Let me share with you in the chat so you can explore. Okay, and then you need username and password. I will share here. Actually, the idea to use this is not you download the images um, from the interface. You can access. I'll show later. You can access all of the data using a Python API, which is easy. Okay. So there is right now there is one bucket. Okay, and then so the data here, it is the consolidated data, all of the CSV files that I mentioned earlier. Okay, and for the cutouts, you have all of the, so for example, if you're interested to the fit files, you'll find all of the fits files here. So let me show, for example, the CS82 fits files. So all of these are cutouts. You can go here and download. Of course, you have to know the JName, but you can, if you have the tabular data, you can easily access to this. I'll show later in the other materials that are prepared. But if you want to go, so we have also processed cutouts. This is ours. This is the cutouts that we process using Trilogy. So for example, if I go to Hypers Prime Cam images, there are a lot of images. It takes a little bit to show some. And then, so for example, let me see. Yeah, I want to see the image of the system, for example, in the complete image. I can go here and see preview. So the strong lens system you can see here is clearly on the center, but you also have the image in for each band, each photometric band, and it's RGB. Sorry, it's in black and white, but here you have the RGB file as well. Okay, but we also make available to you the process cutouts in from Legacy Sky browser. If you don't know, let me go to Legacy Sky browser. You can the DESI survey, they provide this browser. You can you can see for different layers in different tiles many images of the sky. So they process all of these images for you. They also provide the fit file. However, I'm not sure if it's the same original fit file that it's available. So maybe be careful. But so we also obtain the data from Legacy Sky browser, and then we make this available to you because so in some cases we didn't find cutouts from the objects processing by ourselves, so we use their they process images for more make more complete for you. Okay, so I'm going to show here. Let me go back to repository. Okay. Okay, so this is very rough. I show very quickly how the repository is structured. So if you have any experience with Git, you can go here and then click in the copy, and then you open, for example, VS Code. And then you can git clone the repository. It will download everything for you. So I already have the repository here, but let's say I don't have it. So I think I have to make this thing bigger. I think. You can basically git clone. Okay, yeah, of course. The repository, and then if you did not enter in the GitHub yet, it will probably ask you username and password. If you do have any questions, please let me know on the chat on there. Please, you can interrupt me anytime. If I'm going too fast, please let me know too. So it already downloaded the repository, and then if you want to, make any improvement, please let me know. Also, if you want to add other source of data, you can create an issue here in the GitHub. So for example, I think if I remember, someone mentioned this system that was discovered by James Webb Space Telescope. So I just create an issue here to add in the future. I put in the paper here. You can give me any feedback. Okay, and then fix. Okay, yeah. So we have bugs, and I think I already fixed this. I'm not sure. But if you want to include any source of the data, you can just create an issue here. And it's very easy to just go here, new issue, and then say, hey, add this system here to the database. And that's it. It's very simple. Okay, so if you go to the repository again, I mentioned two notebooks. So the first one is located on the data, and in this how-to notebook, I show how to obtain the data from the MinIO system that I mentioned earlier. So I already have. Let me close this. So okay, I cloned the repository, and let me remove this folder because I don't need it. So I already cloned the repository here. So I'm using VS Code. And then if I go to 02 data, and then I open this notebook. Okay, this is weird. Oh no, okay, I deleted the wrong folder, sorry. Maybe some things will broke now. I hope not. Yeah, this happens. Sorry about that. Maybe I think the only thing that will broke is the dashboard, because I accidentally yeah, sorry about that. This shouldn't happen. Let me see. Yeah, it will not work the dashboard right now because I accidentally broke the folder. I put it on back at the end of the session. But at least the MinIO service is still working, I hope. Okay, but okay, let me see. So in this notebook, you see how to access the data. And basically, you need to install only this MinIO package. And if you're familiar with Python, you can use pandas as well. So let me start here. So if you have problem to see, let me make it bigger, because if you're in the, I think it's better. If it's small, please let me know too. I'm also looking in the chat. Okay. If I go to it, yeah, so I have to load all the data here. And then let me see if it's working. It's showing the bucket here. So now how can we obtain the data from the database? Basically, if I run this cell, I show all of the columns from the database. Let me close here. And if you remember, database, I have all of the systems that I mentioned in the database. So here it concatenates all the data from the literature. So there are a lot of columns, and but since the database is not too big, you can load on your machine easily. And if you want to download a single object, so the way that I'm showing here is not downloading anything. So there is no data downloaded. It's only loading the data from the in memory on your computer, but you can use this fget object. So you go to this. This is the where the data is located in the bucket, and then here where I wanted to save it. So if I run this command, it will download it here in the folder for you. So you can use this all of these methods from Mineo to download the data, but you don't have to. You can load in the memory, and you're good to go. Yeah. So if for example, if you use Google Colab, you can only load the data in the memory, and you can only export what you need. So here I want to find associated JName from a specific object. So for this part, I will focus on extracting the images of the cosmic horses hole, which is I think you probably already know. It's this system that looks like this. I know that in the literature, the JName this is the identifier, right? So I want to know in a database where can I find this coordinate? So I want to match this this name here to the JName because with that I can obtain all the callouts for this object. So I can perform a query like such as like this. And here I'm using regex. So if you don't know, if you know regex, each of these terms here, it's blocks of patterns that you can access. And here showing, so if you're looking for this object in the database, the main key is this one, right? And so I'm looking for only the information from the system. It's located in this index here in the database. So here it shows all of the information available for the system. Again, since this system has data in many other catalogs, so each member here is a list of lists. So I use the symbol here to gather all the information together, and it has a lot of references that mention this object. I want to transform each of these that object in a string, in a list. Sorry, and then so for each object that has this JName, it will appear like this. So it's a list of lists, and then so each entry it relates to a single reference. So for example, here actually there are only three information available. So only three reference of the database mention the cosmic horses hole. And so for example, this reference here says that the redshift is 0.4457. I think probably is the master lens database. It says the same. and that the last reference says the redshift is 0.444. Okay, so we know how to retrieve the index of the object in the database based on the previous JName from the literature. We also can obtain the spectroscopic and photometric data available. You can run here. So I'm showing only the photometric match from the system. And again, if I want to search only for this single object, I have this information available in the SDSS, Legacy, data release 9, and Delphi data release 2. And I have all of the photometric information available. And again, if I want to see all of the photometric information available for the system, I know the iLock position, the index position, and then with pandas, I can use the iLock to see all of the photometric information available. I can do the same with all the spectroscopic information available for the system. And so for the system, the SDSS obtain the spectrum for the object. So this is the spectroscopic redshift of the system with this velocity dispersion, with the error, and in the redshift, the error in the velocity dispersion, and other spectroscopic information, and also in between the spectroscopic match. So here we always obtain the useful information. So for example, if you want to go to the Sloan GTSky survey database and then using the survey ID, this is the exact information of the system. This is very useful. For example, if you want to obtain the spectra, the observational spectra of the system, and you can do, for example, test the modified gravity using the data from Earth, which we did this and I mentioned this on Tuesday. And finally, this is the most useful because this consolidated information. So again, if you use the single JName, this will have a single entry from this catalog. And here it shows only a single information for the system. So all of this, we always get the reference and the errors, for example, right? So, okay, so I show very briefly how to obtain the data from a single object that you find in the literature. And now let's obtain the cutouts. So again, we can use this min.io information to obtain the fits file. And here it shows this fits parquet. This is useful because we can extract all the cutouts available in the database for the system. And this means that we can obtain all the fits files and the processed files. So we already discovered that this is the JName. So I have only data from the Legacy Sky survey available, and I can obtain the fits file. And then if I run this cell here, it will download all the data, right? And if I want to obtain the processed cutout file, I will run this. So let me. So currently we have all of these processed files, which so is I think it's a PNG file. And if I want to query for the system that we are interested, I have, let me see. Okay, so, if I perform this query here, I have only 12 files available. So probably one of each photometric band. And if I want to download all the files here, let me, I don't think I defined this. Yes. I think I probably define this file path here. Okay. Let me download a single file. So for example, I want to see the 4 arc minutes image RGB from Legacy Sky browser. So I will add something in the query. So I want this chaining and is RGB equals true. I want the processed image. So I don't have this. So this is false. Okay, so there is an image available. I want the cutout size of 4 arc minutes, but and cutout size equals 4 arc minutes. I have 3 images available. Okay, I want to download all of these images. So I'm going to this loop, so for file in file path, please download these images. Actually, first let me do something more naive. Print file path. So I have this file path here. So if I run the next command, it will create inside of this folder processed cutouts for arc minutes legacy, and we'll download all of these images for me. Okay, it's already downloaded. So it creates these 2 files here, folders, and this is the processed image from Legacy Sky browser, which you might find this way. And actually, this is ours, the way that we process the image from the Legacy Sky browser. And then if you go to Sloan, you probably see something like this. And if you see the Legacy, something like this. So, okay. Of course, I'm going fast, a little bit fast, but you can go to this notebook and try to debug and understand exactly what these functions are doing. If you have any questions, please let me know. I will be very happy to help you on that. So the next application that I'm going to show it to you
Sorry,
is.
I- Yeah, I have a super basic question. So you've been querying the catalogs, right?
Yes.
And I mean the database of the images. So the fact that you're being able to query that way, you have some catalogs that are on FITS format. I saw that one is in the Parquet format.
Yes.
So is the way you are able to query specific to the FITS file or to the Parquet file format?
Yes. So actually, the way that I created this fits Parquet file is only that I list all the objects that it's available in the MinIO system, because the indexing will be faster. The only reason that I create these fits Parquet files was to indexing the files faster, because it's easy. It's faster to read a Parquet file. If you can list all the objects in the bucket, but this take a long time because there are a lot of images and data there. So if you're already indexed all of the objects in the bucket and save in a file, then it will be easier to retrieve the data faster.
Okay,
So
thank
I think it was a way to retrieve the know exactly where the data it is, because you can query faster than so because you can list the objects using this client, and you can list the objects, but this will take longer. So I create this indexing first because it's easier, and then and I think, let me see, if I use this fit catalog here, let me show again the head. This one. So yeah, so I have this. So for example, for each object, I have the JName. In the fit Parquet files, I have the survey, the size of the cutout, the band available, the tile, and the file path. This file path here, it's related to the bucket, right? I can list the bucket. I don't have to do this, but in this way, it make it faster to query the tabular data and the data available in the bucket. So I can add this query here and add, okay, so I want this object, or it could be, so for example, all the images from each survey. I could add, so for example, survey, and then CS82, and then I put and cutout size and so on. With this, I have a list of paths, and then I can loop in this method below here to obtain all the data that I'm querying. So for example, here, in this way here, I'm searching for all of the systems that has processed imaging RGB. So if I put false here, I have all the images in specific bands and the size. And with this, I can ask for the service to see, oh, go to this bucket, go to this cutouts, and then file path is the file path, and download the image in the file path. This could be other path as well. Okay, okay, let me move on to the application, because this will be very useful if you want to perform create a proposal. Okay, I think this is very confusing. So, okay, this is the tree from the repository. If you go to 6 applications, and then the next folder 02 proposals, you see one proposal, IPython notebook. For this, you probably have Matplotlib, NumPy, and Pandas. You can add TKDM if you want. Actually, I'm not using this. It says I'm not using this import, so this is not useful. Okay, I add this to make things in Matplotlib look like a LaTeX. This is not important. So let's say okay, let me select my kernel. Let's say, okay, since actually this is something that I'm going to remove soon, but right now the data is available in the repository as well, but this is not very useful because it's better to put all of the data in the buckets, but you can load the data from the database. I'm loading all of the data in the consolidated catalogs as well. And let me, yes, they're all, they have the same name, but the main importance of the consolidated database, you have a single value for each entry. And so for this kind of proposal, I think I use this. So we did many follow-up observations using solar telescope, and for that specific proposal, the systems were supposed to have this right ascension of in this range and declination of this. So you can do this query. So I want the objects to be in this range here. I have to multiply by these numbers to be in so because this is in hours, I think this is supposed to be 15, I guess. And the declination is already in degrees. So if so initially we have all of these objects, but since I'm reducing only two objects in this portion of the sky, so this dramatically reduced the database to only 211 systems. So this is very, it's not a lot of objects. So this is the importance of the of this that database, because if you query for, if you want to do a follow-up observation and you're limited by the right ascension in the declination, only 211 systems are available. Okay, the next question is, how many of these objects match with the consolidated catalog? Because we always want to have at least a single information for each object. This will be very useful for follow-up observations. Okay, of course, 211, and this is a consistent check, data without match. Okay, and you can ignore this message here. For this specific follow-up, we want to know find systems that has known redshift of the lens and the source. So from this 211, how many systems have this? Only 10. Okay, this is very critical. Only 10 systems have only redshift and non-redshift of the lens and the source. If I want to remove so only on the source, I can perform another query that I'm interested in. So since we have only 10 systems, I will skip this only system if we have magnitude in the IBAN, because it's probably, let me see, let me just curious, let me see how many systems. Only 6 systems. Yeah. Let's not use this query, and objects in the individual scale. So I'm looking for systems in single lens galaxy. Let me see. Okay, only 6 systems. That's fine. Let's search for cutouts. Okay, so let me, before I search for the cutouts, let me show the data from all of the systems. So let's say I'm going to write a proposal based on this right ascension and the declination. I have all of these systems, and most of them are, the lens are galaxy, were classified as galaxies. And if I drop an A, access equals 1. Okay, most of the systems have only redshift of the lens and the source, and I'm not seeing velocity dispersion. So interesting, but this is fine. Okay, so let me load the cutouts, and I want to query the cutouts for the systems. Okay, so with this query, I'm querying images with 20 arc seconds. and RGB, so processed images. These are the cutouts. And in this portion here of the code, I'm creating mosaics for the objects. So for this, you probably need to create a mosaic folder. So I create this folder here, and let's see if it works. So it generated cutouts for all of the objects. So yeah, so this doesn't mention anything useful. So probably we can discard the system, and this it it seems to be a cluster. I don't know. Yeah, this this seems to be an arc here, I think. Since we have only 6 systems, it's easy to check if you want to keep or remove this object. Of course, we can perform a better analysis to removing the image from the galaxy in the center and see and check if it will generate arcs. Then, or that means the arcs will be visible. Yeah, this isn't that I perform this query. It is not interesting enough to show a mosaic of many objects. Yeah, so the next step, we can merge these RGB cutouts with the consolidated data. And then this will be useful for, so the way that we shared the observational proposal with other researchers were that we create a Google spreadsheet online, and then I uploaded the data in my personal repository. And with this mosaic, it will be easy to show the all the information available to share with others. So if you probably if we work together, probably seeing this Google spreadsheet. So basically, let me see if I can render this. So in the Google spreadsheet, it renders this link here to an image, which is very easy to people access. And since we use the data from the consolidated catalog, you can see the right ascension, declination, and the system types. Of course, I could drop. So this means that this is not a number, so we could easily drop this. We have the redshift of the lens. And if I'm moving, so you have all of the information available for the system. We also have the velocity dispersion for the systems, where the data came from. And since most of people have, I decided to use the archive key because it can link to their paper if it was published in the magazine. So it's easy to access. And you have access to the magnitude in each band, where the data came from, and so on. So with the, no. Yeah, so Yeah, sorry, I probably could be more didactic in the way that I mentioned this, but you're more than welcome to contribute with the project, and especially in with the dashboard, because currently the dashboard, the way it's very simple. So I'd like to know if anyone has any questions, or if not, then I'd like to thank you.
So in case there are any questions. So by the way, Martin had to leave because he had a meeting, and he asked me to continue as the chair.
Mhm.
So okay, so questions either from. By the way, I'm seeing the chat. There's something written, but I do not have access to it.
I can have access to the chat. I think Vitor Ramos. Okay, Martin invited him. So yeah. If you don't have any questions, but if you're interested in looking to the repository and give me any feedback, that will be very useful. I will update the link from the dashboard soon. Because I accidentally removed. But yeah, anyone is more than welcome to help with the project.
Any other questions from here? That's just a comment, something that I was missing from myself. Perhaps part of this instruction would be fine that you sent to us before. Because when I arrived here into to pick everything at once, it was not so. For instance, I had no access to the GitHub. I just asked to have access. Now I have, but in the beginning I didn't have it.
Yes, yeah. I should mention this earlier. Actually, part of the talk was I could make it because I have access to the cluster only today, so I have to set up everything on the last minute. So I apologize about that. But yeah, so if you don't have access to the organization, the CosmoOps organization, please let me know. I can include you here, and then you can have access to all the repositories in the organization.
Okay, okay, so very nice. But by the way, my comment was more for the organization than for you. For help everyone. But okay, so if there are no more questions, so let's thank Hannah again. So
Thank you.
okay, so and now we have a coffee break. By the way, to be a larger coffee break, I have to see the schedule up to. Sorry, let me see. Yeah, it should be up to 10 and 50. Yeah. So okay, so we join here 10:50. So see you. Yeah, probably. I think João is in the meeting with Martin, so we have to wait. So hope that will be soon here. So just a moment. Hello. So okay, so sorry for the delay. So Martin and João is arriving. They should be arriving just now. Just a moment.
So sorry for the delay. We were in another meeting about the Last Beru classification with the Lens Zoo Space Warps team. So they gave lots of interesting suggestions. Sorry, it all packed up to be today. So anyway, now, so you heard from Renan about the Last Beru, how to interact with the database. Now, João will tell us about a process that we are carrying on of classifying the systems that were that are part of the database. And I guess he'll make also a hands-on about that because it's on the Lenzu that's connected to the meeting we had just now. So yes, while João prepares his computer, then I keep talking. So the idea of this part, we'll have this hands-on by João. And if there is time, we'll discuss everything about Last Beru. So like future, if you want to add systems, about infrastructure, computing, what we want to use the results for. There has been a lot of interest in the community on this subject. As you saw, maybe, well, maybe you didn't see, but this Last Beru project is having many branches. So one is just collecting this data, like Renan shown. The other is classifying this data, like good systems, bad systems, systems that have counter images. Well, you heard of many classifications. You hear many classifications that João will present. But then modeling these systems too. So having models for a large set of systems. One thing that I think Renan briefly mentioned, but didn't have time to go through, we also use a sample to select systems that have already the information we want to do the physics, right? So for example, in Renan's thesis, he used the Last Beru sampling without any other new data to set constraints on models of modified gravity using strong lensing. So like on the first day of the meeting, we all had several talks on measuring gamma, this modification of general relativity. And so getting this large sample to measure gamma was one of the applications for Last Beru. Other applications that we want is that as we have a large sample of systems, and now we'll have the classifications, So we can use this also to test and develop machine learning methods for classification, like typical machine learning task. You need a lot of systems. You cannot do that before. We had a lot of systems that are tagged manually, and that's what João will talk about. So once we have a lot of systems that have been modeled, like we heard in the second day of the meeting about modeling, either with neural networks, training with simulations, and doing with like the using the physics, like using modeling software, right? In this case, we have data. It's not simulation, so we cannot train a neural network on the simulations. I mean, the first way we want to do it is model all the systems that are good to be modeled in the sample, right? So provide this modeling. This modeling can be used for the physics, but also now have a large set of model systems that we can now train for the machine learning. So we can think of things like Vitor has shown to us, trained on simulations, and then we do a fine tuning of transfer learning on that on a smaller data set, but real data set. So that's it. So we want to really use the last Beru for many applications directly on science, partly on machine learning. We also been using this data set to make follow-ups, so to look for telescopes to get new data. So it's really a lot of branches and like a big project with many aspects. And that's why we've been talking about for days and days. And if João is ready, yeah, we can go. Thanks.
Yeah, so just give me 1 minute until I share my screen here. Okay, so I just want to begin by just making a quick summary of what I showed on Thursday. So this is essentially a diagram of the strategy that we will be adopting to classify the objects on the last Beru sample. We'll begin the classifications with what we call vetting, and I mean there is only one single option, and we kind of grade a lens image. So there is 4 options and one question, which description represents better the object in the image. And there is definitely worth continuing, might be a lens and no sign of lensing. So in this stage, as I said, we classify the nature, and with the best systems of this stage, we classify different tags of I mean, different properties of the same of the lensing system. So just to this classification is also survey independent, which means that we will be classifying an object in different surveys. So, for example, we'll have one object that is classified also on the HSC and DES. So this will be quite interesting to test the time. I mean, the domain adaptation of a machine learning model, for example. So it's a time-dependent, a survey-independent classification. And okay, so speaking more about the vetting itself. So we have the definitely option. I mean, definitely is a strong lens system, so you can bet a salary on this system being a strong lensing. So there is this option. There is the worth continuing option. So this option is for those systems that you are, I mean, there is an indication of being a strong lensing system, but you are, not 100% sure. We also want to classify, for example, in the vetting stage, we'll be classifying smaller cutouts of 20 arc seconds square, but on the tagging, we'll be classifying not only the smaller cutouts, but also the largest one of 4 arc minutes. So essentially in the worth continuing, option will be, we also want to classify the possibly cluster scale lenses as well, because on the tagging we'll be we'll be seeing we will see a larger cutout. But anyway, I will show this in later. So for now, we have already finished the classification of smaller surveys, the CFHT lens, the CS32, and the RCS lens. And essentially, these are some of the examples of the definitely objects. So we have really good candidates for strong lensing. There are clear arclets and multiple images and arcs and counter images. So these are examples of might be a lens option object. So there is an arclet, a central galaxy, but you can't possibly extract much information on these systems. So you choose might be a lens, and there is this no sign of lensing. So no sign of lensing at all. So as I said, the both two options, the first options, the definitely and worth continuing, takes one system from the vetting to the tagging, and the other options doesn't. So okay, so with the best systems, we classify different properties of an object. I'm not okay. Okay, so this is the page that the user see. As I said, there's a smaller cutout and a larger one. And I mean, the tagging begin with a question to check if the user agrees with the system being a worth system to make the tagging. So if a specific user choose no, it will immediately go for the next object. But if an user agrees, so we start classifying the lensing features. And the first thing we classify is essentially if it's an extended arc. I mean, there's an extended arc, or if it's a multiplied image, a point source strongly lensed. So the next thing is the lens classification. If it's an early type, a late type, we saw I mean, their early type are basically galaxies, elliptical galaxies, and late types are spiral galaxies with arms and so on. So we also classify the source, if it's a blue or a red source, and also if the arcs are contaminated or not. This is especially interesting for the modeling later. And we also classify the environment, and this is why we have a larger cutout. And finally, we classify the image quality if there are any dead pixels or artifacts in the image and this sort of thing. So we are also trying to document as much as possible. So you can click on this button and see more information on each of the options and also on the questions. And now I will show the page itself. So just 1 second. Oops. Okay, so this is the homepage of the project. I'll send a link on this Zoom chat in case you want to check. Right. Okay, so this is the homepage of the project. If you scroll down the page, you'll see the available. Also, there's so you see the available surveys to make the vetting. So as I said, we have already made the vetting on the CS82, RCS lens, and CFHT lens. So if I click in one of these surveys, let's see. So for me, it will show as already seen because I have already classified this image. But yeah, this is the page. So there are essentially these small buttons in here. So this first one, you can invert the colors of the image. This is particularly useful for faint arcs. So let me change the survey. I mean, this is the CS82. It's let me change to a colored one to show a little bit better. Yeah. So you can click on this button and invert the colors of the image. Ideally, you could click on this button and see more information, but I mean, it's not set. You can also, you know, make a zoom on your image. You can rotate your image and also reset the zoom level. You can, you know, move if you made a zoom on your image, so it helps a lot. You can also favorite this object, so it will save on your profile on this universe. And yeah, so for these options, for this case particularly, I don't see any sign of lensing, so I will choose this option. Let me invert. So yeah, yeah, I also don't see any sign of lensing for this one. Maybe there is an arclet in here, but yeah, anyway, no sign of lensing. Yeah, so here we have a clearly an arclet and a possible counter image. So, well, I won't bet my salary on this system being a strong lensing, so I will put worth continuing. And yeah, this is pretty much how it works. The vetting. Also, let me. So if you see, for example, an interesting object and you want to discuss more in detail, or you know, start a conversation, you can, you know, classify one object and click on Done and Talk. So if you click on this, it will open like a forum where you can post some comments on a particular object. So for example, if it's an interesting object, let me put here. And you can add your comment. And yeah, it will be on the talk session here on this universe project. So yeah. Okay, so let me show now the tagging. Okay, so with the answers for these smaller surveys, we made a quick statistics around the user answers. And with these quick statistics, we selected some of the best objects in these smaller surveys. So this is one example of one system that was classified as definitely or worth continuing as you know, as a mean answer for the group, for the smaller group. So the user see a smaller cutout and a larger one. You can and also make a zoom on your larger cutout, and it's quite so okay. So as I said, there is this first option to see if you agree with this system being here, being on the tagging. Okay, so I will proceed with the tagging. It will now classify if it's whether an extended or multiplied image. I will put an extended because, you know, we have an arclet. So in this option to classify, so if you choose the extended source, you can classify other properties. So you'll be classifying if it's a single arc, an arc with multiple peaks, has counter image, or if it's a Einstein ring. So and also on this on this question, you can also choose more than one option. So I'll put there is a single arc, and for me, there's a blue spot near the central galaxy. So I'll put has a counter image. Not sure if Martin agree, but yeah. So now the lens classification is clearly an elliptical galaxy, an early type galaxy. So I'll put from the source, it's a blue source. You can see the blue arcs. So I don't see any contamination on the arcs as well. So I will put no. Oh, and also the documentation that I showed. So you can click here and, there is a small text. We're, trying to improve this documentation, but it's already can give you some hint on each of the questions and options. The environment, I would say, I would put it. It's a lens with neighborhoods. So I'll choose this option and click next. The image quality seems okay, so I will choose okay. And yeah, when you finish, it shows a quick summary of each of the options that you choose. And yeah, you can check if you still agree with your answers. And yeah, click next, and you go for the other object. So yeah, I think that's essentially it. So do you think do you want to add some comments or Martin?
Well, just to say that everyone that's interested on joining this is very welcome. As so João mentioned the two stages of this classification, right? The first is what we call vetting. So we start with this large sample of systems, and many of them, maybe like 90%, are not good strong lenses. So we just want to get rid of them. And then there is the second phase of the tagging, where we really classify those systems that are lens in categories regarding the lens property, like the lens galaxy, the image property, like the shapes, multiple images, the source property, like color, environment, and image characteristics, right? So this is like a more detailed classification that we do on the subsystems that have passed the first rounds. So it's 2 rounds, right? The second round is something quite new in the literature. The first round is like every survey of arcs does this kind of classification, right? In our case, the difference is that we start with a compilation of systems that already have a probability of being a lens, very heterogeneous and very large. So still it's new, but this kind of analysis is sort of like the standard thing. But this detailed classification, this is like the first time it's done in the literature. And again, we will be able to train like machine learning models for categories that they have never been trained for. But we need some people labeling, it's like every machine learning image classification, you have a lot of humans putting labels. So that's the thing, right? And this works in several stages, because we also have, besides the 2 rounds, we also have different surveys. And also it's the first time that like different surveys with different images go through this process in the same way. But like users will do one survey like CFHT lens, then they will do another survey like kids. And the same system may be seen like a good lens in one system and not in the other one. So you learn from that. That's also useful for domain adaptation if we want to have like a model that adapts to different image quality. So again, has some machine learning applications. So anyway, so this is like the interface that João has built on top of the Zooniverse platform to carry out these 2 rounds, many stage classifications about all these imaging projects. So if you want to get involved on that and you are not yet involved, just reach out to João or to me, and you'll be able to to join. We'll have like a little training ground. That's some of the things we were discussing. This project has been how we say has been started by us, but now it's been discussed also on the strong lensing science collaboration of LSST and discussing with the space ward people. So we are like learning from those that has a lot of experience, and that's also an opportunity of everyone to interact with these people too. So anyway, if you're interested, reach out. And I think I think we can open to questions, comments. Yeah.
Just by curiosity, so how many evaluations you need? You need some people to label then as there is lens, there is not, etc. How many do you need?
Yeah, so this was essentially something that we're discussing in a meeting that we're having now. I mean, there is a person in the Strong Lensing Science collaboration that did a similar project than this one that we are trying to set up for the last Peru sample, and what they saw was like having there is a sweet spot for users to classify in one specific object, and what they checked was like 8 or 10 users for one object in order to have statistics around the answers. Yeah,
So for each object 8 up to 10.
Yeah, specialists on
Okay.
strong lensing.
So, and the total number of objects that you'd like to evaluate to be how many?
Yeah, so it's 100,000 objects, roughly speaking.
Yeah.
Yeah.
So okay, so you hope there's some time. First of all, these people that will evaluate these are scientists as well. These are not open for
Yeah,
outside the scientific community.
it's not open yet, but we were also discussing on involving also the collab. I mean the other volunteers that don't have necessary a background on strong lensing and.
Perhaps I don't know how to say students of iniciação científica. They'll be probably the best ones to target.
Yeah.
Okay. So,
Yeah,
okay.
that's
So, thanks.
Because-
Just for me, I would like to understand more of the context, etc.
Yeah.
Thank you.
So thanks for the question. Yeah, further comment is that so this is like a multi-stage because there are surveys that have very different number of objects. So we started with surveys that have less than 1,000 or around 1,000 objects, and that's you do it on an afternoon because it's quite additive and it takes a very low time. So you're clicking, so that we can count on specialists. Then there is like another set of surveys. So the first set is like RCS lens, CFHT lens, CS82. The second stage, which is like kids, DES, HSC, it's more like few thousand, maybe like 5,000. So still something that's one person can go through all of this. Then it starts growing, and like with the legacy is about 20,000, and we didn't include other surveys like Delph. So as we learn on doing the smaller surveys with like professionals, we also intend to be adding non-professionals. And you mentioned iniciação científica students, that's for sure. Also in the Zooniverse project, or especially in Lens Warps, which is a citizen science project, they have like specialists on their own, like highly skilled citizens, but they have a lot of experience and they know who they are, so that we can include them in like this third phase, for example, right? And like thinking about sustainability of these as we go to other samples and LSST, then we should open up to the broader community. There's a way to be training the people. And so there's a full paper on that if people are interested, by Karina Rojas, 2016, I think, no, more recently. Wow, there is a paper that studies using the space warps data, like how many views you need, how different, like a professor working on lensing, how different are his or her classifications as compared to a citizen scientist. So all this is discussed in a study. Like no one did this full tagging thing like we are proposing, but the vetting, yes. And so there is a full paper exploring like how people react differently to the classifications. But one of the things we discussed in the meeting we had earlier this morning was these multi-stages of growing progressively larger surveys and also progressively including more people. Like the small ones, we did like Eduardo, João, myself, we did all the systems. We were only 3. For the middle size, we expect to have all the strong lensing science collaboration, maybe about like 20-ish people. And okay, so people need to see half of the systems if we want to have 10 scores. But for the larger systems, probably we need to involve more people. So that's a project for the next few months. Okay, any other question, comment on that part, the classification? All right, so now we have a few minutes to discuss like more generally the Las Peru database. So if people, again, I think we discussed all the from building to applications, many aspects on the Las Peru. Of course, we want to ask people who wants to get involved if they want. And some of the questions we have, or at least I have some of the questions on this project is, well, on one hand, how we want to extend it. So how we want to update it, how we want to include new surveys, make new cross-match. So it's a little bit about sustainability. Like, okay, Renan has done this amazing job, and now he works for an industry. So he's not like the person that would be devoting a lot of time to that. But he has all these tools, they are on GitHub, etc. So like we can inherit and learn. So that's one of the things, who we keep updating this as the field progresses, right? The second thing is about database. Like as you saw from Renan, we have like 5 tabular data with the systems, with the cross matches, and with the consolidation. So this is like a big table. Oh yes, it's a nice Parquet file, maybe nice for indexing, but it's not truly like a database in the sense of IT people. Do we want to do that? What is the solution for that? Do we want a server like physically to host this service? So there are a lot of things connected to the database. And third is how we feed back all the new information that we are producing about the systems, like modeling of the system. João has modeled over 150 systems. He has these numbers, how they go back to the Las Peru. We'll classify a lot of the systems, so we want to keep the classification. So this keeps growing. So how to feed back the information. And last but not least is how we collaborate with similar initiatives in the community. There are other initiatives. They have things in common with us. I think maybe we are the most ambitious in terms of broadness. We do many things with this. We want to collect a lot of things, so it's really like a very broad, very comprehensive thing. So that's, I would say, our strength. Other projects have other strengths, like they are much better in the database sense. They have a system where people can contribute with their own data sets, etc. So there are other initiatives. How do we merge, interact, collaborate? So I think these are like 4 points for discussion. If anyone wants to say anything.
So I have some doubts about the database because I mean it's very promising because it's a very good framework. So my doubt is what's the main idea for the future in the sense of making SL Comp and Raspberry user friendly while keeping it alive so it's not become that like the master lens database has become. So what are the ideas for that? Is there the possibility of the rubbing, the LCCT? I don't know, maybe could find some space in the cloud to command the Raspberry database. I don't know.
Yeah, I just want to comment some uh, about the the viability of the database for the LSST and so on, because we I mean, I think last week we participated on a meeting on the SLSC, and we saw a lot of different efforts for building different databases with different purposes and so on. So I'm especially also concerned on how we could standardize all of the, some of these databases at least. And for example, if we found an object, there is we could have like an interface where we can click on one button and make an upload on different databases that is currently available on these different websites and different databases. So this is something that I think people on the SLSC, especially on the LSST, is trying to work on and standardize all of these databases. But yeah. Okay.
Yeah, so I think your question, Eduardo, was about how to make this not die, right? I think the solution to that is turning this into a community project, not like an individual project. And that's why I think, well, this has been done with LSST in mind, because the data is mostly ground-based images. Of course, we can extend the concept to space easily and maybe apply to Euclid and so on. But like our interest started with ground-based images. So our natural next big project is LSST, period. They are not others. So we really think, and the name tells everything, right? The last stand before Rubin. So that's really something as a preparation for LSST. So I think if we put this in the framework of LSST, which is a project that will last 10 years, at least, I think we are done for the next 10 years. I mean, we are happy. And I don't think a project must last so much, maybe it's fine if it dies after 10 years. So I think that the key to sustainability is this to be part of LSST. And as I said, it's not the only effort. I don't worry if we lose a name. I mean, if we merge different initiatives, there is one called SLED, Lens something, cats. I mean, there are other things. This is SLComp, Lasberu. I don't mind if we merge on something which has a new name and gets the community together. But I think one thing, has to be a project of the Strong Lending Science Collaboration. And I think that's the solution for that not to die. And on the contrary, to be kept up to date. That's a constant source of students, researchers, and so on. Yeah, I think that's a solution. And then we may like buy a server for that. In terms of hardware, I don't think that's a problem. We at CBPF, we are doing pretty well in terms of hardware. Of course, we have very good internet, so to be a hub, that's no problem. And we have a storage. So this is not so much data. I mean, it's enough data to be kept locally on a storage. We don't need very sophisticated solutions. So that's something we can offer. And of course, everyone wants to offer a service because they feel like they put the institution. So other institutions on LSST are also interested in offering this kind of thing. So yeah, I think we just have, I think the most important thing, in my opinion, is to avoid duplicating efforts. So to avoid people doing the same thing, but rather complementing, getting together. And I think that's the main concern, like building something coordinated with the community so that we do the same thing. Each one can specialize on their own stuff, but that would be, I think, a goal for the Strong Lens Insights collaboration. Let's see if we achieve. It's being discussed, right? It's not clear how it will evolve. But I think I would be happy that way. I mean, you can always think bigger, you know, Euclid, WFIRST, Roman Space Telescope. There are many, you know, but I would be happy already if this is just for one survey, which is long, you know. Any other comments?
So this is kind of an unrelated question, but you talked about other projects like this, and something that I've been looking for is something like this, but for cluster weak lensing, like a database of clusters and the source redshift. Do you know if there is anything like that?
So yeah, regarding cluster weak lensing, the situation is basically that for doing cluster weak lensing, you use 3 data products. You use the clusters themselves, so some cluster catalog. You use some shear catalog, and you use some photometric redshift catalog, right? So these data products, they come on their own way. So each survey produces 1 or more shear catalogs, and it's done for everything like galaxy lensing, cluster lensing, shear, whatever. So it's like a product very broadly available. Same for photometric redshifts, everyone uses, and same for cluster or group catalogs. There are sometimes many. So these are like 3 major projects of a survey, especially like LSST or DES. So there's not, I don't think there is any like combination ready for doing cluster weak lensing. I think people, if you're doing cluster weak lensing, you get a cluster catalog, get a shear catalog, get a photometric redshift catalog, and do your analysis, right? But if you're interested on that, like we had students that have done exactly that, right? So for example, Maria Diana, who was PhD student here, and now she's in Germany. She's been also in Michigan, etc. She worked a good deal of her time doing cluster weak lensing analysis. First in the CS82, which is a smaller survey, then in the dark energy survey. So I'm sure she would be happy to talk to you if you want. She has, of course, a lot of code, you know. So Maria Di Diana, I think it's a nice contact. Of course, in SSC, there are many people doing that. I think in general, the atmosphere in SSC is quite friendly. So sometimes when we start a project, we are kind of lost, like, oh, so many people, so much things to do, you know. But I think LSSC is quite helpful with people. But if you want to start with someone like familiar, I recommend talking to Maria, you know. Any other comment, question? All right, so I think we are good to go to lunch, but just hold on 1 minute. So just an announcement about the program. So this afternoon, we'll have the hands-on by Vitor Ramos on using AI for lens modeling. So this is just right after lunch, 2 p.m. So probably it will take about an hour, the hands-on activity, maybe even less. So after that, we'll have like the discussion and questions about that topic, and also a discussion session on projects in machine learning in general, and lensing and machine learning, right? So for those interested on that topics. But as we mentioned, there is a possibility of parallel activities. So there will be a parallel group discussion on the effect of the cosmological constant on lensing. So that's been some subject of discussions in the literature. It's a bit connected to what David presented, right? It's a bit like a cosmological connection to lensing. So there has been a discussion about this in the group. There are several papers. So I think that it's a rich discussion. Maybe to summarize, You have a lens there, it's a point thing. You have lambda everywhere, and then you have bending of light. So we know that cosmological distances are relevant, and of course lambda is included there. But also the integral of the mass may have some like deflection. Anyway, I think it's a rich subject, so it's rich for discussions, and there will be a parallel session about that. So if anyone online is willing to join this discussion, please let us know. So this discussion will take part will start at 3 p.m. So people that want to attend Vitor's hands-on, they can attend. And at 3 p.m., they can go to a breakout room and have this discussion. So this room, we have 2 rooms at CBPF, so we only have to decide which one of the 2 available. And if anyone online wants to join, let us know. If no one online joins, there's no remote connection. If someone online joins, we'll provide connection, and we'll carry on all this discussion on Slack. So if you're interested, write on Slack. We'll send you the link through Slack. We will let and so on. Right? Okay. So we break for lunch now, and so we are back at 2 here for the hands-on on machine learning and regression on lens modeling, and then we have at 3 the parallel discussion on the influence of lambda on lensing. And in parallel to that, we have the discussion on machine learning in general and lensing. Thanks a lot. Bye-bye.
actually this cell here, the one that installs the simulator, and this cell downloads the configuration file that we'll use to simulate the training images. So you can just run all of these cells here, and you can run this one too, because this is the one that runs the simulator, and it takes a while for it to simulate. So while it is simulating, you can click on this folder icon here on the left, and if you double click the training configuration file .yaml, you'll see the configuration file for deep astronomy. And this is where we set all of the parameters for the simulation. I think we have time to go through how the file works, but I left a link somewhere in the notebook, probably around here, with more information about this, because there's a lot to do with these files. So we start by choosing how many simulations we want. I set 4001 because it always ignores one of them. So if I set 4000, it would give me 3999. We set the name for the folder. This won't make any difference since we're saving everything on memory. And the seed. This is also very important so that we have everyone here has the same simulations. We need to set some cosmological parameters with the Hubble constant and omega med. And we start to set the parameters for the galaxies themselves. So we start by setting the parameters of the lens galaxy, the deflector. And deep astronomy divides the galaxies into two models, the light profile and the mass profile. So we start with the light profile. We chose a Circic ellipse. And we set the magnitude for all of the lenses. So as I said, this is going to be pretty simplified. So all of the lenses will have magnitude 18 on all bands. And changing this, other than changing them for all of the galaxies, if you wanted to have different magnitudes for each band, this is a little bit more complicated. With deep astronomy, you would need an extra file that tells it how to do it. So for simplicity, we'll be doing this. It's not very realistic, but the general idea is to have a model that works so that we can increase complexity as we need it. So other than that, we set also the center of the galaxy. The lens galaxy is going to be centered right at the center of the image. We set parameters related to the Circic ellipse, so our Circic and Circic index. We do give them some variation, so these aren't set, they're a distribution. In this case, we're using a normal distribution centered around 6 with standard variation of 0.5. Yes?
Just a simple question about this kind of configuration file. So any parameter in this configuration file for deep astronomy, if I want to have a distribution, can I write it that way? For example, if I want some offsets in X and Y, let's say, so I want the distribution, can I just write the same way as below with a distribution of X and Y?
Yes, you can do this for every parameter. To do this, you would have to, did I simulate already? Yeah, I simulated already, so I'm gonna change it here, but I won't save. You erase the X, the value that you had, and you just copy this exact thing and paste it here. This is what you would have to do. I'm sorry, it's not right. It has to be here. It is very sensitive to the way to the spacing here. So if distribution was written here, it wouldn't work. This is very sensitive. It has to be at this exact tabbing. Otherwise, it won't work. But you can use other distributions. I'm using normal distribution. I could use a uniform. I think there are other more complex distributions as well, but generally what we use is uniform and normal. If you're using uniform, you need to set minimum and maximum instead of mean and standard deviation. Sorry. Maximum. So minimum, let's say 3 and maximum 9. And this is how you would change it. Actually, this is the X value, so it couldn't be this much. It would be very far. So a more realistic value would be something like this, from -1 to 1. And this is really stretching it. -1 to 1 is very, it's a very large range for this. But yeah, you could do this for any parameter of the galaxies. So these files are, as I said, very sensitive to spacing. So if you might get errors if they're not spaced right. So have that in mind. If it gives you an error, it could be this. It could very well be this. So we set the Cirsic parameters, and now we have the ellipticity of the light profile. Again, we set a distribution for this. These are complex. I forgot what they're called. It's a complex definition for the ellipticity. I can look it up somewhere. I don't remember how it is mathematically at the top of my head, but deep astronomy requires these two parameters. It is definitely described in this link here, how these two parameters work. We follow with the mass profile of the lens galaxy. We chose a singular isothermal ellipsoid. And here's where we will set the parameter that we're trying to infer. So for this notebook, I trained the network to infer the Einstein radius of these galaxies. And we're using a uniform distribution between 1 and 4 arc seconds for these galaxies. It's just a value that this is the value that we're trying to infer. We also have the ellipticities and the center of the mass profile of the lens galaxy. And then we can set the values for the source galaxy. Again, we set pretty much the same values with a slightly higher magnitude so that it is slightly dimmer in the image. We give it some variation on the center, both X and Y, so that the source is not exactly behind the lens galaxy. And we have some variations on other parameters as well. All of them have distributions. And here we see the mass profile. The mass profile for the source galaxy is not a requirement in all versions of deep astronomy. It became a requirement at some point, but it doesn't do anything. It doesn't alter what the image looks like. It's there mostly for coding reasons, so that things are compatible. So everything here with the mass profile of the source galaxy is mostly, you can mostly ignore all of this. You need to set it. It needs to have a value, but it won't change anything in what the simulation looks like. So once we have our two objects well defined here, we have the geometry section. And the geometry section essentially is where we tell the simulator that the lens galaxy should be in the closer plane and the source galaxy is in the farther plane. So this is what we're doing here. The redshift value here doesn't necessarily do anything with the simulations. Okay, this is again one of the complexities of working with deep astronomy. It doesn't change anything with the images. It's just a value that is set for the way that deep astronomy is going to output this as a truth table. So this is again kind of like praxis. You don't have to set realistic values here because they won't affect the image. And lastly, after we set actually, wait a second. The important part here is that we set our simulated lens galaxy in the first plane and our simulated source galaxy in the second plane. This is what the important thing about the the geometry section. So lastly, we have the parameters for the instrument that is going to be observing these galaxies. So we're using the Delve configuration. Deep astronomy has a lot of built-in configurations, but and you don't need to set this on the configuration file. And the code that runs the simulations, you can specify here survey equals Delve, and it'll work. But I wanted to keep this here so we can see that we have what parameters we have. So we have exposure time, the number of pixels in each image, pixel scale, PSF, read noise, CCD gain. These are the kinds of things that we can set for the observing instrument. As I said, there are presets for many of these values. So for instance, the seeing is we don't set a specific value. We use Deepland Astronomy's built-in function delve seeing that takes no parameters. So it works with what is expected of delve. You shouldn't just believe this. As I've seen developing this work, this isn't always realistic. So you can't just trust this at face value. You kind of have to check to see that everything works, even though Deepland Astronomy says it does. It's always a good idea to double check everything that Deepland Astronomy says. So now we have the simulations. It took us about 2 minutes to simulate 4,000 images. So we can continue. Yes.
Question. You said that we don't have to trust every parameter that's on lens astronomy. We have to check. But how can we check if the parameters are working correctly, if they are set correctly?
It's what I meant when I said that isn't exactly about if the parameters are set correctly, is whether these things like the delve seeing distribution that Deepland Astronomy gives us, whether it makes sense, whether it's realistic, because it generally isn't. We've seen that for our case, when we try to use our model, the one that we're actually using to try to work with real images, if we use the delve seeing distribution for the seeing parameter of Deepland Astronomy, we won't get realistic results. So we have to make our own custom delve seeing distribution that actually is much more akin to the real distribution of seeing values in delve than this one that they gave us and said it is for delve. So this is what I mean.
But how can you check? You make a histogram of these values in the simulated images, or?
Yes. Actually, you don't have to simulate and then check these values. The delve seeing distribution is a file somewhere in Deepland Astronomy's files. So if you look it up, you'll see that distribution. You don't have to simulate and then get it back. But you check this by plotting histograms and seeing that they don't match. You need to make your own. So since we won't be working with real images in this tutorial, it's fine, it'll work. So let's continue. The simulator outputs this training dataset variable. And the training dataset variable will have inside of it, we'll have two things, the images, the configuration one images, and the configuration one metadata. So the images is pretty self-explanatory. It's a NumPy array with all of the images. As you can see here, the shape for it is 4,000 because it has 4,000 images, 4 bands, and 87 pixels in each direction. And the second thing that we get from the training dataset variable is the metadata, which is this pandas data frame that you see here. It will have a lot of information that we won't use, the majority of it. So what we're going to be working with, the real parameters that we're going to be working with is just the plane 1, object 1, mass profile 1, theta E, G. So we can run these cells here. They will just plot what was already there. And here we can see the image. Yes. Oh, yeah, I had already checked this before. I thought I changed it, but it seems I didn't. So image IDX here. Yeah, so this will plot all the four bands. As you can see, it's not realistic. That's not the point. But right now, this is what will work with the hardware that we have and everything, all the limitations that we have here. I didn't want the training time to be 15 minutes, 20 minutes. So I'm doing this, yes.
So you said you fixed the seed, but not everywhere, right? Probably Landstronomy doesn't have a fixed seed.
I fixed the NumPy seed, the NumPy.random seed, and within the file, the configuration file, there is a seed as well. I fixed this one too.
Because I got a different.
Yeah, so probably somewhere within Deep Astronomy, it uses some other seed that it doesn't set. It's not an issue. I've ran this without the seed before. I probably won't break anything, but we can continue. I think it's not going to be an issue. So this is what our simulated galaxies look like. You can change the number here to see other galaxies. I'll change to the same number. So there we go. I'm printing the Einstein radius as well. These images are very blurry. I don't remember them being that blurry before, but that's fine. I think it will still work. So this concludes the simulating section. And from now on, everything I say can be used outside of lens modeling. From now on, this is kind of a tutorial on simulation-based inference. So if you have any other field or any other application where you can simulate data and have the parameters that you use to simulate it, everything that you're going to see from now on is going to be useful for that as well. So simulation-based inference is, as I said on the talk and on Tuesday, simulation-based inference is a form of likelihood-free inference. And the idea is that we don't want to rely on an analytical form for the likelihood, because it's either too complex or it's too hard to model or whatever. You just don't want to use a likelihood function. So instead of using a likelihood function, you use a simulator. And the simulator needs to be stochastic. It needs to have some variation for a set of parameters so that it actually behaves like a likelihood function. And the goal of simulation-based inference is to allow us to make parameter inference and to get uncertainties for these parameters. So instead of just getting a single value of just the neural network just outputting a single value, it's going to output a probability distribution. And there are many ways to perform simulation-based inference, but we're going to be focusing on neural posterior estimation, which is a very direct form of simulation-based inference. We're going to be modeling the posterior distribution directly from the prior distribution of the parameters and this likelihood, or in our case, the simulator. Other forms of simulation-based inference target other distributions, like you can try to reconstruct what the likelihood would actually look like, and it would be called neural likelihood estimation. And you can also do what is called as neural ratio estimation, where you try to reconstruct the ratio of the likelihood function to the marginal of your distribution. So these methods work very well too, but they're not as scalable because they rely on Monte Carlo Markov chain methods. So if you're trying to make inference for a lot of parameters, they tend to be a lot slower than neural posterior estimation. To perform neural posterior estimation, we'll use the SBI package. Again, it's something that we have to install on Colab because it doesn't come pre-installed. It takes a while to install. We can run this cell as well with the imports. And well, the first step to create a model for neural posterior estimation is to set the embedding net. Now, this is not a mandatory step for all forms of neural posterior estimation, but since we're working with images, which is a form of very high dimensional data, it's very useful to use an embedding net, because we don't want to be working with all that information. If we can summarize that using a CNN, then everything's a lot faster. You can increase the robustness of your model, because slight differences in the image might not, the CNN might learn to ignore slight differences in an image that wouldn't make any difference for our parameter inference. So it tends to make the process a little bit more robust. So if you're working with high dimensional data, I highly recommend using an embedding network. But if you're using low dimensional data, then it's fine to ignore this step. You don't need an embedding network. So since we're going to be using it, I'll give you a brief explanation of what is going on here. We're essentially setting the architecture for the CNN that will be our embedding net. We will take 4 channels, the 4 bands, with input shape 87 by 87, which is the number of pixels in our image, 87 times 87. And here we set the number of channels in each convolutional layer. So we're going to start with 128 channels. We have this data tensor that would be 87 by 87 by 4, and then after the first layer of our network, it's going to become an 87 by 87 by 128 tensor, which so it's a very big, a much bigger tensor. These are called feature maps of the image, and the idea here is that we're going to have the neural network is going to scan your image in groups, and it's going to detect features in that image. So maybe straight lines going up, straight out lines going sideways, or maybe curved lines. This is what each of the 128 feature maps is going to say. It's going to tell us where in that image do we see a certain feature. Since we have 3 convolutional layers, we're going to have to set 3 numbers of channels. So we start with 128, then we go down to 64, and then 32. And after the 3 convolutional layers, we're going to have some linear layers. In TensorFlow, it's called dense layers, if you're used to that. These are just classic neural networks layers. It's just fully connected layers. We're going to have 4 with 256 parameters each. And then finally, one important step of using an embedding net is the dimension of the output vector. So we start with this 87 by 87 by 4 image, and after the CNN, it's going to become a vector with 16 dimensions. So essentially a 16 by 1 matrix. And this is pretty important. The number of points here is something that we test when we're running models. As I said, on my work, we're using one network for each parameter that we're inferring. And this is one of the things that we change between the 4 parameters. We found that, I don't remember exactly which parameters use which number of dimensions, but we allowed this to change. So some parameters might use 4. So for instance, the velocity dispersion, the ideal number of output dimensions would be 4. Maybe for the Einstein radius, it's 16. And we check this by testing. We essentially run the model with 4, with 8, 16, 32, and we see the one that gives us the better result. So for this, I set 16 because it works. If you want to change it, you can. But I don't recommend doing it now. If you're going to do it, wait until everything ran and then come back and do it again. So we set the embedding net. We're going to instantiate the embedding net object. And then we're going to set what kind of density estimator we're going to be using. So neural posterior estimation works by using a density estimator to learn the relation between the posterior distribution that we're trying to infer and the likelihood distribution multiplied by the prior distribution, which in our case, since we're using simulation-based inference, is then the output of the simulator. So we sample points from the prior distribution of our parameter, which is, as I said, it's in the configuration file, and we simulate those images. So we're trying to learn essentially the relation between the image and the posterior distribution for that image. And we're going to be using normalizing flows to do this. Normalizing flows are a class of density estimators that use neural networks to find invertible and differentiable transformations that you can apply to a base distribution, like a Gaussian distribution, something simple that you know how to sample from, and then we apply those transformations to this base distribution to try to make it look like a more complex arbitrary distribution that we're trying to model. Normalizing flows, and we will apply what we choose in normalizing flows is the kind of transformation that we will apply, and the parameters of these transformations are what the neural network learns. So it learns how to transform your initial Bayes distribution, your simple Bayes distribution, so that it looks like the distribution you're trying to model. And for this, we're going to be using neurospline flows. Neurospline flows are a class of normalizing flows. It's a pretty interesting class because it pretty much slices your original distribution in several small parts and then applies a slightly different transformation to all of these parts. If you're interested in learning more about this, I left these two links. They're a bit complicated to explain, but they work very well. And the general idea is this that I just described here. So if anyone's interested, you can check these two links. They have very interesting material. But we're going to be using neurospline flows. So we set NSF here for the model. We tell the posterior object to use the embedding net that we defined earlier. And here we choose the number of features and the number of transforms. So the number of transforms is the number of transformations that we're going to be used in our neurospline flow. So essentially we set 2. This means that we start with a basic Gaussian distribution. We apply a certain complex transformation to this. It becomes a second distribution, and then we apply another transformation because we set 2. This is a small number, relatively small number. For more complex models, I've used 8, 16. This is something that we check. We run many different values for this. We try models with many different values because it definitely affects the result a lot. And hidden features means the number of parameters in the neural network that defines the transformations. So as I said, we start with the Gaussian, we transform it into a second distribution, and this transformation, the parameters for this transformation are defined by a neural network. What we're saying here is that the neural network that chooses these parameters has 8 neurons. It's a very simple neural network. Again, this value is not very realistic. We use much larger values for more complex models, but it works for what we're doing here. So we can create the neuroposterior object, and the neuroposterior object is going to be what our density estimator, and this is what we pass to the inference object. So in this cell, we're telling them the model that we're going to be performing neuroposterior estimation. In this case, SBI calls it sequential neuroposterior estimation, but this is not true. For this to be sequential neuroposterior estimation, it will require a few extra steps that we won't be taking, and I'm not taking at my work. But essentially, the difference between SNPE and regular NPE or amortized NPE is that sequential neuroposterior estimation focuses on a single observation. So if I had one real image that I wanted to model, I could kind of optimize the training process to be very focused on that one observation. But this is not what we want. We want a model that works for a large data set of observations that isn't focused on a single strong lensing system. So we're going to be using what is known as amortized neuroposterior estimation. But in SBI's implementation, it's still called sequential. This is not very correct, but this is what we use. So we set the inference object. And now next step is to prepare the training params and training images to be used here. So what we do is expand the dimensions because what we had a tensor, let me see here, with shape 4,248. Wait, 248, this is not right. Oh yeah, it is right because this is the number. Okay, so it had 4,000, and since we're using only the Einstein radius, it would be 4,000, 1. We need this one dimension to be explicit, otherwise it won't work. And this is because simulation-based inference, wait, where was I? here. And this is because simulation-based inference, in simulation-based inference, you can use many parameters at once. I am inferring only the Einstein radius, as I said, but we could just as easily train a model to infer maybe the velocity dispersion. I don't think this model outputs the velocity dispersion the way it is written. We would have to change the configuration file a little bit, but my point is that it's easy to make inferences of more than one parameter using this method. It has to have this shape, so 4000, 1. If the shape is 4000, it won't work. And it needs to be a torch tensor. It can't be a NumPy array. Again, this is mostly just a technical aspect of what we're doing here. And it's important to move everything to the GPU, which we do by using device equals CUDA here. This is very important because if you don't do this, the training time is going to be much larger than it needs to be. So we run the cell, we have the parameters here, so 4000 images in the dataset, 4 bands, 87 by 87, and a single parameter, which is the Einstein radius. We then load these objects, this data to the inference object, and we can start training. So I'll start the training, and while it is running, I'll explain a little bit about these parameters. Again, I wouldn't expect everyone to know a lot about how neural networks work, but the idea is that a neural network, we'll start with a training set, and we're going to show every single image in that training set to our model so that it learns so that it sets some parameters inside of it, which are called weights. So it learns what are the ideal weights that would cause this image to output, cause this network to output a certain value when you show it that image. So an epoch for a neural network is one pass through the whole data set. So here we're setting 200 epochs. It's a relatively low number. I don't think we're going to get even close to that because it's probably going to converge much earlier than that. But you could set a much higher number. I think I usually set this around 3000 for the models that I'm using. And stop after epochs is essentially something that we use to decide when the neural network is sufficiently well trained. Here, it means that if we don't see an improvement in a loss function over 20 epochs, then this is when we stop. To be clear, again, 20 is a very low value. It's not good, especially because training these models the training process for these models tends to be very unstable compared to other neural network models. So if you're using this for a more serious application, you could have much higher values here. I would easily set this one to 200, this one to maybe 2000, 3000, and this is what we would expect to work. The batch size is essentially the number of elements in the training set that we're going to be using per pass of the neural network. As I said, an epoch is when you look through the whole data set. The batch size is essentially how small and how many times we divide this data set before showing this to the network. We show it to the network in small batches. In this case, we're showing it in batches of 512. The learning rate is essentially how much a single pass of the neural network affects the weights in the network. So it's at 0.01. It's a relatively high value. You could set it at much lower, but your training times would be a lot higher. And the validation fraction is essentially what percentage of the training set we're going to hide from the neural network during training so that we can evaluate the performance of the network in data that hasn't been used to train it. So we're using 10% of our test set. So we can see here my networks converged after 76 epochs. This number varies. As I said, it's very unstable. So we can plot it here. Let me see what it looks like. You see, you have these peaks. It's common. If you have any experience with neural networks, you'd expect this to be a very bad model because of all these peaks. This is not really expected to be a good training plot for a regular neural network. But as I said, training normalizing flows is very unstable. So these variations, it's hard not to have these variations, and I believe they won't affect our model in our case. So let's move on. This is what it looks like. So over the 70 epochs, our loss function is the log probability that the true value for an observation is sampled from the probability distribution that the model generates. This is what the log prob is. It's negative because we're minimizing it, and it's log because of numerical reasons for numerical stability. So essentially, the loss function here is just you just ask the question, how likely it is, if I show the model a certain image, how likely it is that it's going to predict the true value. So we increase the probability over time. The negative log prob decreases as the training moves on. This is what this plot is telling us. So finally, we can build the posterior object. This is what we're going to be used to sample from the posterior distributions. So the next step is to evaluate the training model. To evaluate the training model, I'm going to give you another file, another configuration file that uses exactly the same parameters as the other one, but it has a different seed. So the simulations are going to be different. They're going to use the same parameters, but they're going to look a little bit different. And we're going to simulate here. For the test set, I'm only using 1,000, so this should 1,000 images, so this should run a lot faster. And it's going pretty fast. And we're going to run this cell too, which is the cell that prepares this data to use an SBI. So it turns it into a tensor, expand dimensions, the same things that we did the other time, except for this, for the test set, we don't use the GPU. We use the CPU because it doesn't make a difference now. So the CPU is going to be faster. I think SBI is going to even raises an error if you're using the GPU here. So just set it to the CPU and be happy. We can analyze a single image. We can pick essentially any image out of our test set. As I said, there are 1,000, so you can set any number here from 0 to 999, and it's still going to work. And we're going to take samples from our posterior distribution. So what we do is that we tell the model that this image is the one that we want. So test images is our array of images. We're using the third element in this array, so the third image, setting the default X for the posterior for it, which means that we're showing this image, and we're going to take 1,000 samples from this. And what this is doing is we're taking 1,000 samples from the posterior distribution given this image here. As I said here, there are 1,000 samples of the distribution, and this is what it looks like. So what we have here is the probability distribution, and an empirical probability distribution for this image that our model outputs for that image. And the red line here is the true value that was used. So as we see, the peak here is not exactly at the true value, but it's pretty close. And we can set different numbers here. So we use 30 to see how it looks for other images in our test set. So this one is pretty good. It's right at the center. We could set 300, and we'd see other values. See, this one's a bit further. It's not a problem that this is further. We'd expect, depending on how far it is, we would expect it to be that far, depending on what the posterior looks like. And there are steps to ensure that the number of true values that fall very far from this is acceptable. So as we'll see in this notebook. So we can do this for the whole data set. We can generate posterior distributions for the entire data set. We do this with this loop here. Essentially what we do is generate these samples we're generating 500 only instead of 1,000, so it's a little faster. We're gonna save the samples distribution. We're going to also save the median of this distribution in a different list. So this is what the prediction actually is. This is what we interpret as the prediction. We're going to save the 84% quantile, which is the value for the 1 sigma, the upper bound of the 1 sigma interval, and the 16% quantile, which is the lower bound of the 1 sigma confidence interval. And we're also going to save the percentile of true, which is the score. When we have this distribution of measurements of posterior samples, and the percentile of score is going to give us in which percentile the true value falls. So if we have a plot like this one, essentially we're going to be at a very high percentile probably. So we're kind of far from the center. So at the other one, I think it was 30. This one is really close to the center. So what we would have here is like probably somewhere around the 50 percentile. This would be the score, the percentile, the score of this true value and this percentile. So this is what we're saving here. So we saved these lists, we turn them into arrays, and here we plot what our true versus predicted plot. So essentially, each point here is the measurement for an image. On the x-axis, we have the true value. And on the y-axis, we have what the network predicted for that value. And what we see here is that most of these values fall very close to the x equals y curve, which is what we want to see. It means that if I simulated an image using 2.5 arcsecs as a value for the Einstein radius, most of the images that have this as a true value have this as the predicted value as well. So our network is working as we expected. We're going to do some things here to turn these results into a pandas data frame so that we can make a slightly more sophisticated plot that gives us the 1 sigma confidence interval, and this is what we see here. What we do in these data frames is that we bin our distribution. So essentially, we divide this range of 1 to 4 here in 30 bins. And for each bin, we take the average y value, so the average predicted value, and this is what sets this green, maybe yellowish line here. And we do the same for the sigma plus and sigma minus, which are the upper and lower bound of the 1 sigma interval. So we take the average value, and this is what gives us this plot. So this is essentially a binned version of this plot here, and where we plot the 1 sigma confidence interval as well. And as we see, it follows even for the points that are somewhat farther from the x equals y curve, we have our confidence interval still covers it, except for the very low bound here and maybe at the very high bound here. But overall, there's no systematic predictions that are overconfident, or sorry, not overconfident. They are not higher than they should be systematically. So this is not a curved. We don't have like a curve here. It's following the x equals y pretty nicely. And finally, we can report precision and deviation for these measurements. So we have what we do here is essentially we calculate the precision as this here, 1 minus the width of the error bar divided by the values, and the deviation is the distance between the true value and the predicted value as a percentage of the predicted value. Actually, it should be as a percentage of the true. It depends. You could set it as a percentage of the predicted or of the true value. It would have a slightly different meaning, but These are two ways that you can set the deviation. So we define these two functions, generate points in our data frame for this, and then take the mean values for these distributions here. And we end up with this, the median precision, which we get that is 86%, which is a nice value, and the median fractional deviation that is close to 5%. So we would expect, for looking at the whole set, we would expect the precision to be centered, the precision value to be 85%, 86% actually, and the fractional deviation to be around 5%. So the last step that we have here is simulation-based calibration, which is an important step because it allows us to assess the quality of the posteriors. That is, it tells us whether we are systematically generating posteriors that are either overconfident or underconfident. And what this means is that an overconfident posterior is a posterior that is narrower than it should be. So for like, if our model, we would expect the posterior to look like this, a model that generates overconfident posteriors would generate posteriors that are closer to the true value than they should be. So it's essentially giving us uncertainties that are lower than they should be. And of course, an underconfident model does the opposite of that. It gives us wider uncertainties than it should. And we know what kind of uncertainties we should expect because as we sweep the range of our values, we should expect values to fall in a certain range, a certain percentage of the time. So essentially what we're doing here is we are analyzing different areas of our posterior, different intervals of our posterior, and seeing how many times the true value is contained within that range. So for instance, the 20% confidence interval means that we're looking at the interval between the 40th and the 60th percentile of a posterior and counting how many times the true value for that posterior is covered in this interval. So if our model was well calibrated, we should expect to see 20% of our values here. What we're seeing is slightly less than 20%. So it's through the whole range here, it's slightly less than it should be. This means that as we increase the confidence interval, we're seeing less empirical coverage than expected, which it means that this is underconfident. The posteriors that our model is generating are slightly larger than they should be. This is usually not a big issue. It's a bigger issue for the opposite. So when it is overconfident, it means that our uncertainties are lower than they should be. This here means that the uncertainties are slightly higher than they should be. And to correct this, we would have to change parameters of the network. We would have to, ideally, we'd have to simulate more images and run our training with more images. But I think we're close to the limit of what Colab offers us. So we're kind of limited here by the hardware. But this way we can assess whether these uncertainties are reliable or not. Finally, we have a few other steps that are related to what is called rank statistics. And it's actually, the idea here is very similar to this. The rank of a posterior is essentially a count of how many samples from that posterior fall below the true value. And the general idea here is that we want the rank distribution over our entire set to be uniform. We don't want to have any variation in it. So we employ a few tests to check whether it is like a uniform distribution or not. Specifically, we run the KS p-values test, which essentially tests whether they are the same distribution. It gives us the probability that a set of points taken from the rank distribution and a set of points taken from an empirically uniform distribution are taken from the same distribution. And generally what we want here is a value that is non-vanishing. So, okay, this here is a vanishing value. This is 4,000 times 10 to the minus 7. This is a very low value, so we didn't get a very good result here. Essentially, what this says is that there's a very low chance that these are the same distribution, which is somewhat expected since we don't have a perfectly calibrated model here. So we do need to go back here and change some stuff in our model. I ran this same parameters before, and I've gotten better results. As I said, the training process is very unstable, so your results may vary. But generally, you're seeing it live here. It failed, but it's not a big deal. The KS value is kind of it's a check that we employ to decide whether we want to go on or not. So if the KS fails, that means we get a very low value here. The model's not good. But if the value were, say, above than 5%, that doesn't mean that it is good. It means that it's not bad. So you can continue to check for other things. We have the classifier 2-sample test, which is essentially a test in where we train a classifier to differentiate between an actual uniform distribution and your rank distribution. And the idea here is that we're going to see the accuracy of this classifier when trying to differentiate the two. And we want values that are close to 0.5, so 50%, which would mean that the classifier cannot find the difference between the two. We're seeing 60%, which is not terrible, but it's not good either. It's not perfectly calibrated, but it's also not a terrible result. If your model is slightly worse than this, you could expect to see classifier 2-sample values that are much higher, like 90, 95%. And finally, we have the actual ranks distribution. This is what it looks like. As I said, it should look like a uniform distribution. And in gray here, we have the 99% confidence interval for our uniform distribution. And what this means is that for each bar here, for all of the bars here, we would expect 1 out of every 100 bars to fall outside of this region. Here we have 50 bins, so we have 50 bars. We shouldn't see any bars falling outside, but as I said, as the model is not perfectly calibrated, we're seeing like 4 bars falling outside of this distribution. So these are the tests that we employ to see if our model is calibrated or not. As you can see here, this one isn't perfectly calibrated. It's not a disaster, but it's not perfectly calibrated. What we could do here to try to get a better result is to change around these values here, the values for the training. So we could set maybe a higher value for the patients. We could set a maximum number of epochs. We didn't even get close to it. We stopped at 76 because we probably our best validation value here, log prob validation value was probably at epoch 56. After that, it didn't see an improvement, so it stopped training. And we could use a higher value to see if we can keep decreasing this value. We can keep improving our model over the training epochs. We could use different batch sizes, which could probably make our model more robust. It would be trained on smaller steps of data each time, so it would avoid local minima in the training process, and we could have a lower learning rate. That generally we expect a low learning rates to help with these oscillations. As I said, it's very unstable for neuroposterior estimation, but a lower learning rate would help, but it would also make the training time a lot higher. So if you're interested in trying out different values, I highly recommend you do. As I said, make sure you're using a GPU backend and not a CPU, otherwise it's going to take a long time. And I guess this is what I had for today. This is the general idea here. I think I covered all the bases. The main difference between what is done here in this tutorial and what I did for those values that I showed on the talk on Tuesday is the number of transformations. we're using many more transformations. We're using neurospline flows, as I said on the talk. We do use the same normalizing flow that we're using here, but we're using more transformations. We're using a much larger data set. We're using a lot more variation that we're doing here. These two configuration files are pretty simple. We use much more complex ones that involve extra files that map try to tie together different parameters so that we can have different magnitudes on each band, obviously, and different redshifts for different magnitudes, and a lot more variation than it is being done here. So another important step that isn't covered in this tutorial is the preparation of the images. Deep Blue Astronomy outputs them in units of ADU. So essentially, it's a count of electrons here that were generated by the observing instrument. In our preparation, we do flux conversion so that it's each pixel is a unit of flux. And then we do background removal, which for this scenario is not very important because we don't have anything in the background. And finally, we do normalization, which is a mathematical step that helps with neural network convergence. So if you have any questions about this tutorial, please feel free to contact me on Slack or wherever you find me. I'll be happy to answer any questions whenever you do it. If you haven't ran the notebook right now and you want to run it later, it's fine. I'll take questions even after this is done. And so thank you for watching.
Thank you so much. It was very interesting. Questions, comments?
Hi, Vitor. Thanks for the hands-on. So if I understand well, you are training your the model in a simulated data, right?
Yes.
So the way it's now, so you're using the parameters from the simulation, but for example, let's assume we want to train with real data, with lens parameters, with uncertainties and so on. So it will be possible to use the uncertainties as inputs for this kind of model or covariance matrix and this sort of thing.
It might be ignorance on my part, but I don't think you can input uncertainties for the training process using neural posterior estimation. Neural posterior estimation is a technique of simulation-based inference, which means that the goal of it is to train only on simulations and not use any real data. And once everything is trained and validated and you know that it works, you just apply this to real data and see how well it performs. From a technical standpoint, I think it's possible to do this. I don't know how, but I don't believe it's fundamentally impossible. But it kind of falls out of the scope of what simulation-based inference does.
See, thanks.
More questions, comments? Any question from those online? Don't see any hands raised. All right, great. So thanks a lot for the hands-on tutorial. That was really interesting. So now what we can do is we go for the break. The break is there. So those that want to go for the parallel on the light deflection by cosmological constant, then you meet in room 215D, and Davi is already there. And those that want to discuss applications of machine learning to strong lensing, that we can stay here after the break. So for what is broadcasted of this meeting, this is over. So we will stop broadcasting, which means we stop recording. And so from now on, it's only discussion sessions. We will still keep the Zoom connection, so remote participants can continue, but that will not be recorded anymore. So that's the end of the recorded part of the meeting. Thanks for attending. If anyone is watching online, okay. So let's go for the break. And thanks again to Vito. Well, there
Thank you.
seems to be perhaps a question.